solids are just
and molecular solids are individual molecules. Mm-hmm. So the bond within them is covalent, but the bond between them is just intermolecular forces. Right? That's all. And ionic network solids are just big dumb rocks. Yeah. Big dumb rocks.
Big dumb rocks.
Yes. Okay. And so I've been teaching it for years, right? Okay, so let's get to it. Alkanes, alkenes, and alkynes of fun. What the heck does that mean? Yes. We're going to talk now about organic chemistry. If you were here yesterday, I had you beginning with a little introduction to organic chemistry. Really quickly, what is organic chemistry? Somebody give me like the brief rundown who started yesterday saying, yes, my friend.
Isn't it mainly like chemistry with like carbon and oxygen?
Yep, and the other big one?
Hydrogen.
Good. Yeah, absolutely. That's true. Organic chemistry is the branch of chemistry that deals with compounds, covalent compounds, that have carbon, hydrogen, and oxygen as sort of their base, as sort of their spine, if you will. That doesn't mean that we won't see other atoms. We will. But carbon, hydrogen, and oxygen are the sort of central piece. Why carbon and hydrogen? Why is carbon end up being this central molecule or the central atom for life? You are made of lots of things, but just about every molecule in your body is carbon-based. We call, yeah, go.
It can make 4 bonds.
Okay. Sure. Why are you not going to build complicated 3-dimensional molecules out of oxygen as your starting point? Why would oxygen not be a good thing to use if you're trying to make complicated 3-dimensional molecules? Anybody? Bueller? Anybody?
So I'm not really this unit because organic chemistry was my nemesis in university.
Me too. And it's funny because now it would not be. It's amazing how. But seriously, why carbon? Why would oxygen be bad? Well, oxygen tends to make how many bonds? 2. If oxygen's making 2 bonds, are you going to be able to make a lot of big, complicated 3-dimensional structures? If you keep putting them together, what could you get? You get chain, right? It'll just go on forever, right? Not a very effective way to build a 3-dimensional shape. On the other hand, if you start putting carbons together, carbon makes 4 bonds. Now we know they're actually at what angle to each other? 109.5, but I'm just going to draw it this way for simplicity's sake, right? But we know that tetrahedral arrangement, right?
3D problem for 3U trig.
Oh, yeah.
Because it's like a tetrahedron,
right? Exactly. Yeah. We'll talk. Cross-curricular. But if you see, when you start going here, you can build however you want. Do you want to keep building this way? Just keep adding carbons. Do you want to branch up here? No problem. Just add carbons. Right? Now, the thing to remember is that every one of those carbons is going to make how many bonds? 4. Okay. Again, you'll get the odd case that breaks the rules, but mostly things will make 4 bonds. sp3 hybridized. Great. Okay, cool. Now, the only problem is, if that's the case, if we're building this way, then how does it stop growing? Am I that boring already? I respect it. It's okay. Are you okay? Do you need a drink? Oh, I'm sorry. Well, if you...
It's been through the hallway.
So it's not me. Okay. Okay. Anyway, if I can help you, let me know. Now, the problem with this is, if you keep just connecting carbons to each other, you will eventually get, and you should have just learned about this in your independent lesson from last unit, eventually you'll just get diamond or coal or graphite, right? Whatever, just keep growing out. So if you want to make a complex 3-dimensional shape, you have to be able to keep branching off, which carbon is great for, because you can keep branching off in any direction you want. If you want to make carbon atoms into a big, thing that made the shape of the letter A for your initials, if your name started with A, you could do that. But how do you get to stop? What caps it off? Hydrogen. See, if you put a hydrogen here, hydrogen only makes 1 bond, and so any place a hydrogen is bound essentially acts as a cap. It stops that molecule from growing in that direction. So this right here that I just randomly put together, that could exist. There's no reason that couldn't exist. And so if we knew how, if we have the right technical know-how, we can make that in a lab. Does that make sense? Oh yeah, you bet. Yep, back to. Do you want disposables? Or do you want like big rubber? Or do you want?
Disposable.
Yep.
Because there's activity, which means I have to pry them off to hand to the kids. So
Use your teeth.
I used a Kleenex, not good stuff. It was
Oh, I just. Here you go.
My teeth is the best option. Let's not.
And make lots of dog sounds.
Also, a kid that we share finally found his way across the hallway for the first time in over a week.
Well, there you go.
So
He's like, "Am I failing?" I'm like, "Well, we haven't named him. We're good." I was like, "In as much as your mark is 0.0%, yes, of course you are." So that was good. It was a little bit of a wake up. He's like, "Really?" I'm like, "Yeah, no, of course." So he's good. So I'm like, "Do you have these things?" And he opened his backpack, and they were like
everywhere.
a miasma in this. I'm like, "This is good. We can put these in a binder. You can hand that in. We can mark it." So I think I'm hoping. Yeah. Oh, that's pretty.
Beautiful.
That's very nice.
Well,
that's
good. Well,
impressive.
he showed up today and then
Good.
asked to sit with another kid that he doesn't currently sit with, and I'm like, "You're going to sit in your mom's seat for the lesson, but then when you're working, if you want to go
Nice.
work with him,
Well,
I
that's
have
good.
no problem with that." So
You know, we had a good chat today. He's a nice kid. So I'm
the
hoping that
worst
he's
part is
starting to.
I emailed home this morning.
Well, good. I'm hoping. Well,
Of course.
no, but that's
I emailed
good.
home and put him in
I-
in-school teams, and he shows up.
Well, but that's good. I'm hoping he starts to get the
He's
message.
capable. So
He's a nice kid.
He is.
So anyway, I didn't say a name there, right? I'm recording this right now. I don't think so. I might have to scrub through that and make sure I didn't. I didn't? Okay, good. All right. So anyway, enough about that. So this shape right here, you could build this, but you could also build something much bigger than this. If you've taken biology, you start to learn about the organelles of the cell and all that. They're just big carbon molecules. Your cell membrane is just an enormous collection of big carbon molecules. They're just big molecules, millions upon millions of atoms stuck together in interesting shape. And the machinery of your cells are made of carbon stuck together in interesting ways. And you can literally make your muscles are things made like this that have been designed so that when they receive an electric signal, they change shape and they shorten and they pull up, and that's how you move around. It's all molecules that have been built out of big, complicated things, and carbon and hydrogen make the framework for that because carbon lets you branch out and hydrogen lets you control how you branch out if you were to sit down and design this. Does that make sense? Science fiction movies always postulate the idea that we might find life on other planets that isn't based on carbon, but it's based on a different atom. And what do you think science fiction movies and science fiction books love to postulate as maybe we will find blank-based life on other worlds? Sure, and why do we think silicon might be the one? Because it also makes 4 bonds. Interestingly, silicone, which is silicon formed into things like this, isn't a part of any living things on Earth, but anytime you get something that is silicone, whether it's a spatula or whatever, or mold making or things like that, that is actually molecules very much similar to organic molecules, but instead of carbon being the base, silicon is the base.
Conditioner for your hair, I think, is silicone-based stuff.
Yeah, exactly. And a lot of industrial lubricants are, instead of being carbon-based, they're silicon-based because they tend to be a little bit more, what's the word I'm looking for? Stable. They're not as reactive. They don't degrade over time as much. So, with that in mind, that is the basis of organic chemistry. Organic chemistry is that we're going to start building big, complicated things, but we're going to do it by putting carbons together to make them bigger, and we're going to do it by putting hydrogens on those carbons to stop them from spreading out in every which way. Yes, sir? Good question. No, there'll have to be something, because the most carbon could do is make a triple bond, right? Which means it's still going to have one free bond. So that's a great question. There must be something capping off every organic molecule, typically a hydrogen. It can be something else, and we'll talk about that in coming days, but obviously that's going to change properties. If you stuck a fluorine on there, you would expect different behavior, right? Because now you're going to have a dipole, and we're going to talk about all that. So hydrogen is the default, though it can definitely be something else, and it can't just be an open bond, right?
I think excuse the interruption.
Yeah.
We have Kira Green and guidance.
Kira's not here today.
Thank you.
Is Kate Odette here, or do I have to do my own attendance?
She went on a trip.
Not all of my attendance list. Okay, so this is the basic idea. Carbon makes 4 bonds. Hydrogen makes 1. They combine easily into chains. This is a naturally occurring phenomenon. So one thing to note about the word organic is we sometimes think of it as synonymous with life because the molecules in living things are organic, but they don't have to be life-based. Organic molecules can also just come about spontaneously, randomly, which we know happens. So basic carbon chains form as a result of living processes, to be sure, but they can also be the result of just natural chemical reactions that happen. So just, when you read that we found organic material on another planet, that doesn't mean we found life there necessarily. Now, there's some compelling evidence that some of the have we talked about this? Mars? We talked about Mars? Crazy stuff. Look it up. It's interesting. We have found compelling evidence of organic molecules on Mars that really don't seem like they should be the result of natural processes. That's not a guarantee. Obviously, further studies need to be done. But there seems to be some really compelling evidence for small microbial life on Mars a few billion years ago. Again, evidence doesn't mean proof, doesn't mean we know that, but certainly there's good cause for investigation there. So perseverance, earn and or keep. Percy, doing well. Yes?
So the planet Mercury and the element Mercury, which was named first? Like, what's the
They are both named after...
God or something. I don't remember which one though.
Is Mercury the equivalent of Mars, which is
War?
Yeah. That's right? Like Mercury...
So,
Yeah.
So was it one named after the other?
No, they're both named after a god. Now, is the god named after the planet in the sky?
No.
Very likely. Could be, right? Like, remember, we've known about planets for a long time. The Greeks and Romans knew about all the planets because they tracked the stars and they could tell the difference between the ones that never moved relative to each other and the ones that moved through the sky. So the Greeks and the Romans knew the difference between the planets and the other stars, and they had names for them. So we don't actually know which name, chicken and egg of it all, right? Like, we know that they've been relating planets to gods and the sun and the moon to gods for years, right? So when we talk about the sun and, say, the god Ra or the god Aten or the god whatever throughout sort of history, it's not immediately clear, those people all definitely knew about the sun before they had the vision of their god, because obviously the sun goes up every day. So it's hard to know. It's interesting. That's an anthropological question. I'm not an anthropologist. But... Anyway, so just as an example, if we wanted to make a carbon chain that was 3 carbons long, it would look like this. And on every one of these little bonds, we would have a hydrogen. Just like that. Does that make sense? Okay. Now, that's with 3. What if it was just a chain of 1? 1 carbon. Well, to stop it from growing any bigger, how many bonds does carbon want to make? And what would have to be on each of those? Hydrogen. And this has come up as an example 100 times because it's a nice, easy, symmetrical thing to make. The formula for this, obviously, is SCH4. And its name, does anyone remember? You've mentioned this 100 times. Doesn't matter if you remember it. Methane. Good. So, CH4 is methane. Methane is one of the simplest, well, it's not one of, it is the simplest organic compound, simplest possible organic compound. Carbon is its base, hydrogen is its cap, and it is literally one carbon. It is also a very regular byproduct. The bacteria in your gut produce methane. That's why you can light your farts on fire, which if you've never done, don't let me tell you not to. I remember that being like a regular activity in my high school, but times do change and we didn't have cell phones, so we had to entertain ourselves. Cows produce it. It's a regular greenhouse gas. Now, what if we added a second carbon? Again, how many bonds does each carbon want to make? 4. Okay, very good. And what goes in each spot that isn't a carbon? Hydrogen. So what's the formula of this 2-carbon chain? C2H. Yeah, very good. C2H6. And this has a very clever name.
One question.
Sure.
Why do the carbons not form a double bond?
They could, and we will talk about that. So they absolutely could. In this example, they don't. But here's the thing. Great question. If you can draw it, an organic chemist can figure out a way to make it exist. That's the truth. As long as you can follow the rules, even sometimes if you break them, an organic chemist can figure out reactions to make it happen. So we're going to talk first about single bond, only sigma bond organic molecules, but then we will talk about introduction of pi bonds. Great question. And this name, very clever. Ethane. Very good. And then hane, and then ain, and then neh, and then eh, and then no. Though one could be excused for thinking so. Now, I want to show sometimes instead of drawing this, we would just say CH3 down to CH3. Does that make sense? That's a little cleaner sometimes because this can get kind of messy to draw. Does that make sense? We'll get to that. You're good. So in the next one, we would have CH3 bound to a C in the middle with how many H's and then bound to CH3 at the end. How many H's would the one in the middle have? Because how many bonds does it have free to make? Only 2. Very good. That is a 3-carbon chain. What will its formula be? C3H8. And this is something you're very familiar with probably. If you have a barbecue at home or if you have a camp stove, propane. Don't put gasoline on your barbecue. It's a very bad idea. Gasoline is very volatile. It produces lots of fumes that like to explode. We don't want to do that. Listen, my first period class was a young gentleman who caught fire this summer. He wasn't even putting gasoline on a fire. It's worse. He'd been working on a go-kart. He's like a gearhead. So he was repairing his go-kart and he'd gotten gasoline on his body. And then his buddies were having a campfire. So he finished up in the shop, walked over and ignited. You do not want to, gasoline produces fumes and they ignite at a very low flash point. So if you are going to be, and listen, I lived out in the country. I redneck it sometimes. If you are going to redneck a fire, diesel or kerosene, relatively quite safe because they don't produce a lot of volatiles and they have a relatively high flash point. It takes a lot of temperature to ignite them. Gasoline, dangerous stuff. You want to be careful. So that's...
Assuming there aren't more fires just from people pumping their own gas.
Yeah, I mean, the nice thing is, like, there really aren't a lot of ignition sources there, but it has happened. There have been catastrophic gas station fires. Yeah, there you go.
And then you start smoking.
I love that movie so much.
Do you know I've never seen it?
It's so good. You can watch it. It's like
I've seen that scene, but I've never seen the whole movie. I've heard it's wonderful. I've heard that I would love it. Obviously, the next carbon chain won't be 3, it will be... And how many hydrogens will it have? Yeah, we're getting the trend here, right? So it'd be CH3 to a CH2 to another CH2 to another CH3. I want you guys to fill this part of the chart out. All right, take 30 seconds, get it filled out. It's kind of boring. I will introduce you to another way we can draw this. which is in organic chemistry, we kind of do a thing where instead of this, I could draw this in what's called a skeleton diagram. And in a skeleton diagram, we don't draw carbons. And we don't even draw the bonds to hydrogen. So you'll see this sometimes. So they would draw this. It's 1, 2, 3, 4 carbons. So they would go, there's a carbon, I'm not going to draw it, to a second carbon, to a third carbon, to a fourth carbon. So that would be C4H10. Kind of weird, right? But they just, if there's the end of a bond and there's nothing there, that's assumed to be a carbon, because carbon's the backbone of organic matter. And then they don't even bother drawing the 3 other bonds here, the 2 other bonds there, the 2 other bonds there, and the 3 other bonds there. They just assume that all gaps are filled in with hydrogen. Does that make sense? So you will see this. So this next one, if you want to draw it as a skeleton diagram, would be 1, 2, 3, 4, 5. And remember, you're not the lines are bonds. So you're not counting the lines, you're counting, math term, ready? The vertices. You're counting the vertices.
I was going to say the pointy corners.
The pointy corners, but also the pointy ends. Corners and ends. So this would be 1, 2, 3, 4, 5. And I'll even put that on there. That'd be 1, 2, 3, 4, 5. Or, of course, if you prefer, you could draw that as CH3, bound to CH2, bound to CH2, bound to CH2, bound to CH3. I know which one I prefer, which is the pointy corner one. Way quicker. Right? Love those vertices. Way better. So that'd be 5. We could have 1, 2, 3, 4, 5, 6 here. 1, 2, 3, 4, 5, 6, 7 there. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Again, if you want to draw every carbon and hydrogen bond, like if you want to draw this as C, H, 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 C, you go nuts. I'm not doing that. That's a lot of lines and a lot of H's. But don't let me stop you. Whoa. And again, the important thing to remember when you're counting here is that you're not counting lines, you're counting vertices. Each vertex, if there's nothing drawn at it, is assumed to be a carbon. You don't actually want to put the numbers there. I'm putting that there just for sort of our sake. But I want these filled in as well. Predict what the formulae will be up all the way up to a 10-carbon chain. Surely you found the pattern by now. It's pretty simple, right? What will this one be? Excellent. Okay. Yep. Okay. By the way, we are arbitrarily stopping at 10. This could obviously keep going to 1,000. There's nothing stopping you from having a molecule that is 1,000 carbons long. In which case, if it were 1,000 carbons long, how many hydrogens would it have? C 1,000 would be H what?
2,200.
Nope, close. Is there an extra one on every 100th carbon? Where are the extra ones? Just on the end. So there's two hydrogens for every carbon, and then you get an extra one to cap each end. So it'd be 2,002. In fact, the general formula of this type of chain is CnH. Well, math here, come on. 2n plus 2. Good. All right. That's the generic formula of a straight chain of carbon with only single bonds. And we call these alkanes. So this is the general form of an alkane.
So it's just like a basic carbon hydrogen chain.
That's right. An alkane is a basic chain made of carbon with hydrogen, such that there's no branches on a basic alkane. And they are named systematically. The first few names kind of exist from history, so they're a little bit messy. Methane, ethane, propane. Does anyone know what the fourth one is? If you have a lighter, it may contain this. Butane, and then after this, they get logical. There's no kind of Latin root that you're going to know that meth, eth, prop, and bute mean 1, 2, 3, and 4, but from here on, they're nice and logical. Does anyone know what a 5-carbon chain is called? Pentane is correct.
What do you call those lighters that you can refill with fluid?
Butane, typically.
Is it like Zippos?
Yeah, I love a
What's the
Zippo.
difference between a hippo and a Zippo? One's really heavy, the other's a little lighter.
Oh, I like that. That was good. That was good. Yes, it would. So we have hexane. And then the next one you might not be familiar with. Septane would make so much sense, and it should be, but instead of going for that French root, it goes back to the Latin root, and so it is in fact heptane. I'm sorry, I didn't make it. It should be septane. I agree completely.
Is there like a committee that you thought you
Not
could change?
follow that?
Yes, what a great question. In fact, all naming in chemistry comes from IUPAC, the International Union of Pure and Applied Chemistry.
That is a very entitled name.
The International Union, and the "and" doesn't get a, so IUPAC. It's like Tupac, but
I was
different.
going to say, yeah.
So the International Union of Pure and Applied Chemistry, and they have changed things bigly.
Is there an
The naming that I learned when I was in high school is all out of date now, and it's totally different.
July
Because
should be called September.
okay, yeah, the whole thing is insane. It's insane. It is wild that September is which month of the year?
9 months.
Oh, that 9th makes sense. October, what month is that? Oh, perfect sense. Oh, December. No, November. No, November. Oh, that's the 11th. Oh, December. What month is that? Oh, it's brilliant. It's brilliant. And then, to be clear, if you divided the year into 13 months instead of 12, each would be exactly 4 weeks. And everything would work beautifully, and you would literally have 1 day left over. But instead, we have this crazy system of 12 months that are different lengths, and the less said about the better. It's insanity, right?
The Roman emperors who wanted their name on the calendar.
Pure insanity.
Julius Caesar, July,
Yeah.
and Augustus.
Yeah.
I feel like it makes no sense.
Where does April come from?
Avrilo.
Probably Julius Caesar's mistress. I don't know.
Yeah, I don't know. I should know, but I don't. Yes.
So this is called the pure association. Is there an unpure?
Yeah, applied. So pure chemistry is theoretical, and applied is literally like working in industry,
I thought
so they deal with both.
calling themselves the best. They were calling themselves the purest form of chemical associations. They were number one. They were the only.
I'm glad that's where you went, and not they're white nationalists or something. But anyway, and then I went there. They get together in their little white pointy hats, and they decide what to call organic compounds. Anyway, was that inappropriate? It's a good thing I'm recording this. Anyway, do you think those morons could figure science out? Anyway, yeah. Anyway.
So, would you say once it hits 5, the naming would be the same?
They get good and logical, yeah.
So
Which means similar. We're not calling this octacarbon octadecahydride for obvious reasons, because that gets messy, but it's going to use the same prefixes.
Would a 42 chain one be a tetracontic hydrocane?
Yes, well played. 8 is obviously octane. Good. C9. Think shopping at No Frills.
Nonane.
Nonane is correct.
Nonane.
Nonane, nonane, whatever.
Where did the T go? Oh, I guess okay.
Yeah. And then 10? Decane. There we go. And then you could go unidecane, dodecane, blah, blah, blah. We're not going to go there. Point being, it does keep going. We're stopping here just for reasons of practicality. Yeah.
So notice all of these are like kind of fuel.
Yep.
Are there any of these that's not a fuel?
These all burn.
They all burn.
Organic compounds, here's the deal. Organic compounds are ripe targets for an oxygen looking to break it apart. Because that's what burning something is. Burning something is just blasting it with oxygen and having oxygen just rip it apart. So if you look at this molecule, if you heat up oxygen molecules so they're going fast, they're just going to tear this thing apart. And the smaller it is, the faster it'll tear it apart. So the trend with these is they all burn. And as you go up the list, the temperature you need to make them burn gets a little bit higher. So methane burns at absolutely nothing. A little spark will get methane going. Same with ethane. By propane, a spark will still do it, but it's got to be a bit more substantial of a spark. Butane lighter, a spark still does it. Pentane, hexane. By the time you get to octane, that's gasoline. A spark often isn't quite enough to get gasoline to burn, though often it is, so you got to be careful. But certainly a flame will do it. Nonane, decane. And then by the time you get to like these longer ones that are 20 or 30 carbons long, it takes a lot of heat to get them going. Even when you just get to something like diesel fuel or kerosene, which is actually just branched. It's these, but with lots of branches, which makes them a slightly tougher target. A diesel truck has to be, you have to be careful that you don't let the engine block get too cold or it has trouble igniting, right? Because it takes a bit more. But that's kind of the basic idea there. Did that answer your question? Great question. Nice. Okay, so this is going to end up being the foundation of all organic chemistry because you, as complicated as you are basically a bunch of chains like this put together in interesting ways so they start getting real three-dimensional. Does that make sense? Because you can start taking one of these chains and tacking it to another chain and tack it to a third chain and just kind of build up around like that. And that's what you are. So the alkanes, the basic chains of carbon, are the building blocks of all organic material, which means functionally they're the building blocks of life. They're the building blocks of you. These are not big dumb rocks. These can be put together in very interesting ways. Because you can sculpt rocks at like the big level, but you can sculpt these at the molecular level. You can make them into complicated shapes, and you can make them into complicated shapes that will actually move and form and do jobs and do tasks. You can make little machines out of these. Your body is full of little machines made out of chains like this put together. And we're going to talk about how. Does that make sense? If I seem excited, that's because this stuff, it's funny. Like Mr. Kelford, organic chemistry was the bane of my existence. Famously, my final exam in second year organic chemistry, I did so poorly that in a class of like 500 kids, the professor phoned me at home and offered me a Faustian bargain, which if I wouldn't take her third year course, she'd give me 50. Because she felt bad that I'd gone for help that week and she had thought I was just nervous and said, I think you'll do fine. And I did not do fine. Really nice lady, Dr. Pauls. And I sucked up my...
60%.
Mine was a 5.0, and I had like a 98 going in, and then I got 17 on the final. And you're supposed to need a 30 on the final to pass. But then my pride wouldn't let me have like a gifty, so I retook it. I did fine the second time. Now at 42, I'd be like, I'll take a gifty %. Sign me up. But at the time, my enormous ego was offended by this. Not enough to have studied in advance, mind you, which is what I should have done. But honestly, I did study. It is challenging. It comes at university. Organic comes fast. This course, organic is people's favorite unit. Usually, it comes at a nice pace in this course. You will probably like this unit the best, is my prediction, because it's neat. It's interesting. Okay, now, the interesting thing about this is we know that every carbon actually makes 4 bonds, which means you can make a straight chain, 10, 20, 30, 50, 100, but anywhere on that chain you want to, you can branch off. Does that make sense? Which lets you start to make things three-dimensional. So if you look here, this is an example of a compound that has a branch. By the way, if we wanted to redraw this as a skeleton, the main chain, the steps to this are, when we want to know what this is, we're going to identify what's the main chain. And usually they'll draw that in a straight line. They don't have to, annoyingly. But if you look here, This has got a main chain that is how long? How many carbons is that? Yeah, it is 1, 2, 3, 4, 5, 6. So the main chain of this is just, what do we call a 6-chain carbon again? Hexane, right? Ane for alkane. When you see an ane ending, that means a straight chain of carbon. So this is like a hexane, only it's a hexane with a couple of things tacked onto it. What's been tacked onto it? Well, it's almost like it's got this. Oh, thank you. That wasn't helpful. This is like a hexane with this thing tacked onto it. Well, what is that thing? That's a methane, right? So this is the hexane, where on the second carbon of the hexane, they shoved on a methane. Okay. And then, what else did they shove on there? Well, on the fourth carbon, they shoved on an ethane. So it's got an ethane on carbon 4. It's got a methane on carbon 2. So if you're telling somebody how to draw this, you could say, make a hexane. Then on carbon 2, add a methane. And then on carbon 4, add an ethane. Does that make sense? If I gave you that instruction, you'd be able to draw this, right? Somebody give me an instruction like that right now, just to show you that it's easy to do. Just make one up for me. Just make it up. Go.
A pentane.
Okay, so I'm going to make a pentane, which is 2, 3, 4, 5. I'm going to hold off on adding hydrogens till we're done. Okay? Okay, and a propane is 1 carbon, 2 carbon, 3 carbons, like that, right? So there we go. Alex just gave me the instructions. I just made it. And then I can fill the hydrogens in, right? How many hydrogens would this have? 3. This one would have. This one would have just 1. This one. 2. This one. 3. This one would have. This one. This one. Okay. And so this, I got the instruction, make propane, right? Make pentane. And then add propane to carbon 3, right? When we name things organically, we actually just name them so that it's instructions on how to build it. Does that make sense? So this is a hexane. So when we go to name it, we would say this is a hexane. And then we would say that on carbon 2, it has a methane. And on carbon, I will it. And on carbon 4, it has an ethane. Yes?
For the ethane, why is it H2 and not H3?
Because if you look at this carbon here, if we were to actually draw this, 1, 2, 3, 4, 5, 6, coming off of carbon 4 up to this carbon, it has to go up to that carbon, right? And every carbon wants to make 4 bonds. So how many hydrogens are going to fit on this one? 2. Does that make sense?
So it's not really like the hydrogen that's identifying, it's the carbon.
Yeah, in fact, like I said, if I were drawing this, I'd draw it as 1, 2, 3, 4, 5, 6, right? And then I would say on carbon 2, we're going to go up to 1 more carbon. And on carbon 4, we're going to go up to 2 more carbons. That's how I would draw that. Does that make sense? Each vertex is a carbon unless something is drawn otherwise. Because this gets clumsy, and you can imagine if we tried to draw this like this, we'd be here all day, right? I mean, you could do it, but it's annoying as all get out, right? And then on carbon 2, we'd put another carbon here with hydrogens. And on carbon 4, we'd put a carbon here and a carbon there. And then I have to come back and I have to put a hydrogen in every one of those spots. And by the end, I'm just wishing I were doing something else, like having my eyelashes plucked out with rusty pliers. Your mileage may vary. But these are 3 ways of drawing the same thing. Does that make sense? They all mean the same thing. I don't care which one you do. If this is easier for you because you can really visualize it, awesome. Nothing wrong with that. Is that anyone not comfortable with that? This can be tricky because you do have to kind of in your head count how many hydrogens it would have, which is why I never add the H's. Like if you saw when I did it over here, I didn't add the H's till I was done, right? Because then it's like count how many bonds it's making and then just subtract from 4. That's how many hydrogens it'll have. Did that answer your question? Yeah? Did it answer your question satisfactorily? Okay, good. Okay, does that make sense? If we were giving instructions on how to build this, we'd say make a hexane and then put on carbon 2 a methane and on carbon 4 add an ethane. Now, all we're going to do is when we turn this into one name, instead of saying on carbon 2 put a methane, we're going to say put a methyl, which just means it's a branch. When you see YL as an ending, that's going to mean this is a branch. On carbon 4, we're going to put an ethane, so we'll call that an ethyl. And then the name will just be 4-ethyl, 2-methyl hexane. That's a single word. All right? Single word, like cat, dog. You can teach your brother to spell. Cat, dog, God, 4-ethyl, 2-methyl hexane. Right? It's a good name. It's a name. You can name your kid that. You can be like, this is my son George. This is my son Larry. This is my son 4-ethyl, 2-methyl hexane. They would probably be the only 4-ethyl, 2-methyl hexane in the class. They wouldn't have to be like, is that 4-ethyl, 2-methyl hexane F or 4-methyl, 2-ethyl hexane G? Yeah.
Why are we not using the Latin prefixes for 4-2? Why are we not saying dimethyl?
We're going to, and di is going to mean that there's 2 methyls, and 2 is going to mean that the methyl is on carbon 2. So eventually we're going to have to use both. You might say, right? Because you might say it's a dimethyl, which means it's got 2 methyl groups. So you might have to say it's a 3,5 dimethyl, which means there's 2 methyl groups. One of them's on carbon 3, and one of them's on carbon 5. So when you see a number, that was a great question. I was just about to make that note anyway. Numbers always indicate location on the chain. Location on the primary chain. So what this name is telling us is you're going to go to the 4th carbon on the chain and put an ethyl group. You're going to go to the 2nd carbon on the chain and put a methyl group. And the main chain itself is going to be a hexane. If I were designing this from scratch, I'd probably have the name of the main chain come first so that you'd know what that is. So when you read one of these, you almost have to read the end first. And you're going to say, okay, it's a hexane, which means my main chain is how long? Okay, then I'm going to draw that. Then I'm going to go to the 4th carbon on the chain, and I'm going to add an ethyl, which is how many carbons? 2. Great. And then I'm going to go to the 2nd carbon on the main chain, and I'm going to add a methyl, which is how many carbons? 1. And then, boom, there are my instructions. Does that kind of feel okay? It's a lot, right? It's a lot. Yeah?
For the situations where you, for example, you want to like draw another structure from like methane or something like
Yep.
that, would it still be the same one? Because what would the number for methane be?
Are you asking if there's like a branch on the branch?
Yeah.
We're actually not going to get to that. There's a whole second, you use brackets. There's a system with brackets. We're actually not going to get to that. It doesn't come up as, like, by that time, things to have more specialized names. But yes, you can have a branch on a branch. They have a little bracket system they use to kind of indicate that. We're always going to assume in this class that everything is branching off of the main chain, which tends to be more true it tends to be a lot easier to synthesize things where you kind of get you don't tend, unless the molecule is very big, to get a lot of branches on branches. So it does happen. And again, we have a naming system for that. It actually goes a little bit beyond the scope of this course. Great question. Yes?
How do we decide which one to say first? Why don't we say 2 before?
Great question. Alphabetical order. Rule of thumb is put your side chains in alphabetical order. So E comes before M. Now, to be clear, if you called this a 2-methyl, 4-ethyl hexane, would I know exactly what you're talking about? Yeah, and you'd be fine. The best name, in organic chemistry, you're going to find that actually there's 1,000 ways to name things. The best name follows a certain set of rules, and one of the rules is we put side chains in alphabetical order as a rule. But again, I'll show you this. If we go to if we go to my favorite place on earth, moleview.org, if we put this in and we say 4-ethyl 2-methyl hexane, it's not looking this up in a database necessarily. This one actually is showing me that it is in the database, but sometimes you'll type something in that isn't in the database and it will still draw it for you because it can just read the name and follow the rules. So look here, 4-ethyl 2-methyl hexane, there's our molecule. And you can see our main chain isn't as easy to find as you might think because, of course, what are all the angles here? They're not 90 degrees like we draw them. They're actually 9.5. So they always have this kind of zigzaggy pattern to them, right? But if you look, the main chain, 1, 2, 3, 4, 5, 6. On the main chain, if we go to the second carbon, we have a 1-carbon branch. That's a 2-methyl group. If we go to the 1, 2, 3, 4th carbon, we get a 2-carbon branch off of it. That is the 4-ethyl group. If we change the name, if you screwed up and you called it a 2-methyl 4-ethyl, what was our main one? Hexane? Hexane? It's going to draw the exact same thing. Does that make sense? Because it can interpret that name. The better name is in alphabetical order, but somebody would figure you out. Does that make sense? So you'll see a lot in this unit. From time to time, I'll say, that's correct, but it's not the best answer. And that's okay. You will learn to find the best answer. How's that feel? Okay. Now, we may have the same side chain appearing more than once, which is exactly the path that Aiden was leading us down. So what we're going to do, first and foremost, you have to find your main chain. And when you find your main chain, the main chain here is going to be the longest chain you can make. Does that make sense? So I could try and call that a chain and everything else a branch, but that's a stupid idea. Why? Because I wouldn't want to make my main chain be only 3 carbons long when there's a main chain I could make that is 7 carbon longs. Does that make sense? Now, you also want to do it so that it avoids having branches that then have branches. If I wanted to, I could make that my main chain, right? I could actually do that. The problem is one of my branches would then have a branch of its own. Now, you could still name that. Like I said, there's a system. It uses brackets. But make your life easy. Find the longest continuous chain you can. And then there's actually a rule. What do you notice about how they've numbered this one? Does something jump out at you as kind of weird?
It's numbered backwards.
Yeah, why would they number it backwards? Again, you will get the answer. You will get a correct answer either way, but there's a rule, which is
I don't know if this is right. Is it because the branches are on the bottom?
not that they're on the bottom, because you can flip this thing up, but you're on the right idea. It's about where the branches are. Basically, you number it such that when you do your naming, you'll end up with the lowest numbers. Because I started numbering here, my branches are going to be on carbon 2, and on 3, and on 4, and on 5. If I numbered it the other way, my branches would be on 3, 4, 5, and 6. So the best name gives you the lowest numbers in your final answer. Does that make sense? Sometimes there is no perfect solution. Either way is going to give you whatever. But if one way will give you lower numbers, that's a better answer. It doesn't mean that the other answer is wrong. It means that the other answer could be refined. Is that fair? Can we try to name this one? What's our main chain? Okay, so what's that called? So this is a heptane. That's okay. Now, this has groups on it. What are the groups? What is this group here? That is a... Yeah, and when it says branch, we don't call it methane, we call it... And I need to know where it is. So specifically, this is a 2-methyl group. Good. This one here is also a methyl group, but it's not a 2-methyl. It is a 3-methyl. All right? There should be a dash there. What about this one here? Yep, 4-propyl and 5-methyl. So that's a 4-propyl group. 4-propyl, and then 5-methyl. Now, if you wanted to, you could call this 2-methyl, 3-methyl, 5-methyl, 4-propyl heptane. That would be allowed, actually, but it wouldn't be a good name. We don't like that name. Instead, if we have 3 methyl groups, like Aiden said, we have a prefix for 3 of something. What's that? Tri. So we could say that this is a trimethyl. It's trimethyl, and where are the 3 methyls? They're on 2, 3, and 5. So if we want to, we can combine all those, and we can say that this will have a 2, 3, 5 trimethyl. Does that make sense? Again, if you wanted to call this 2-methyl, 3-methyl, 5-methyl, 4-propyl heptane, that wouldn't be wrong, but this is better. It's a lot cleaner. Yes?
I'm not going too far with this. What is the suffix anol, like ethanol, methanol?
We'll get tomorrow.
Tomorrow?
Yeah. Great question. We'll get there. So now it's a 2,3,5 trimethyl, and then what comes next? 2,3,5 trimethyl. 4-propyl heptane. You will note that there's no spaces, commas between numbers if they're next to each other, dashes between numbers and words. Does that make sense? I'm going to rewrite that in a different color because I've been using green to kind of locate stuff, but we'll measure it there. So when we go to name this, we're going to say, okay, I have 3 methyl groups, so that makes it a trimethyl. And then where are the trimethyls? Well, they're on 2, 3, and 5, right? And then we have a propyl group on 4, and then no dash or no space there. It is heptane. I would be shocked if this is in the database at MolView, but if we type this name in MolView, it's going to draw us exactly that. Does that make sense? Even though this almost certainly won't be a compound that somebody has saved in there. Maybe it is. Maybe there's somebody out there doing a lot of work with 2,3,5 trimethyl 4-propyl heptane, which, by the way, not a bad name for a dog. I mean, you do you, but if we type this in here, it's going to know how to draw it, because even if it isn't something in the database, this has been trained to know how to make compounds. So 2,3,5 trimethyl, and then what was the other? 4-propyl? 4-propyl heptane. And you will note not in the database, right? See how it's got all these related ones, but it doesn't have this, right? Not showing up. Doesn't matter. It's going to make it. It's going to make it because it knows how to read. And if you look here, it's doing this as the main chain. So there's carbon 1, 2, 3, 4, 5, 6, 7, right? On carbon 2, we have a methyl group. On carbon 3, we have a methyl group. 4 has a 1, 2, 3 propyl group. Carbon 5 has a methyl group. Carbon 6 has no branches. Carbon 7 has obviously no branches, right? Yeah. Yep.
Why is that third methyl longer than the other two?
Because this is based on 3-dimensional space. So this one would be pointing up towards you a bit. So that makes it look shorter. This one would be pointing down away from you. Because again, what are the angles not actually? 90 degrees. They're actually... So if you look here, see how messy this is? Hard to see here, right? Where's the main chain here? Oh, golly. Right? You got to find it. But I would probably count it 1, 2, 3, 4, 5, 6, 7. And then if you look, off carbon 2, we have a carbon back there. That's a methyl group. Off carbon 3, we have 1 carbon in front of us. That's a methyl group. Off carbon 4, we have 1, 2, 3 carbons. That's a propyl group. Off this carbon here, 5, there's a methyl group. 6 has no branch. 7 has no branch. See, it's hard to see when it's a model, right? Can we all agree that's kind of tough to see? Which is why sometimes, even in our 3-dimensional model, that's not better. We'll sometimes do that, right? But it's tricky. Sometimes you can turn hydrogens off, which can really be helpful. Anyway. Yeah.
Is the
Yes, that's the rule. The longest continuous chain. And for the purpose of this course, we're always going to make it the longest continuous chain that allows none of your branches to have their own branches. We're going to prioritize that. So even if your main chain ends up being a bit shorter, but it means a branch doesn't have to have a branch, we're okay with that. But usually it's not that tricky. So here, where's our longest chain? Well, this one's nice actually, just straight across, right? Can we all agree? There's no way to get a longer chain than that, right? Like, that's not longer, and that's not longer, right? And that's not longer. So the best chain here is that. Now, should I start numbering one over here or one over there? In this case, the left or the right? Yeah, why? Good. Would it be wrong if we did it the other way? No, but it would be suboptimal, right? So 1, 2, 3, 4, 5, 6, 7, 8. What is my main chain here? Octane. Good. What's on that octane? Do we have any groups? Yeah, so we've got methanes. And this is a methane on carbon. Did I just skip from 1 to 3? So this is a heptane then?
Yes.
Wow. Not my best moment. I thought I made this question that they were all heptanes. Weird. Guys, what did I think I saw that too. And I was like, oh, there's already a 2 here. Sorry about that. I am so sorry.
Is there a reason why, like, on carbon 6, H doesn't have, like, H2?
Oh, it should. Yeah, that's a typo. Good eye. That's weird. It's not like I made this. I shamelessly stole this. Interesting.
And no planet.
No? So you know, in my biology test, I sourced every image. I put a reference page. Something I'm going to start doing on tests. I figure if I demand it from students, why don't I demand it from myself, right? Almost seems fair. So I'm going to stop being a hypocrite. Yeah?
In like nature, is it more or less like optimal to have, since like there's 2 what are they, like methanes on the same carbon chain, would it be better for it to be like one to be on a different?
Both do happen. Both exist. This is actually this is harder to engineer if you're an organic chemist trying to make this stuff. The interesting thing to know about nature is that, weirdly, like a lot of these molecules, these more complex ones, have to be built by the cellular machinery itself. And so they really are built. They're engineered. So it's interesting to think about that. Engineered isn't the right term. But some things are certainly harder to make happen than others. Some things happen more naturally. And a double branching substitution is less common than a single branching substitution, to answer your question. Did that answer your question? Good. So we would call this a 3 what? That's a 3-methyl. And of course, this up here is also, and it's also a 3-methyl. This has 2 3-methyls because carbon 3 has a methyl on one side and a methyl on the other. And what would we call this group here? 4-ethyl. Does anyone want to take a shot at naming this? Yeah, you want to go? Do your best. You want to do it on the board? Awesome. Yep. Go for it. Love it. Love it.
So we go alphabetically, right?
That's right. So what's going to come first?
Oh, wait, that's wrong.
Cool. That's excellent. It's not quite perfect, but it's really close. It's really, really, really close. That's excellent. Very well done. The only thing is that you've told me it's a dimethyl, but you've only given me one location. Now, you might intuit that they're both in the same place, but they actually don't go for that. Instead, they actually give both locations, and they would call this a 3,3-dimethyl, which may seem stupid, but that's how it's done. They explicitly give the location of both. Otherwise, perfect. 4-ethyl, 3,3-dimethyl heptane. Very good. No offense, I'm going to rewrite that to be a little bit more legible. And I mean no offense. You did a lovely job. So yeah, on the fourth carbon of this, we're going to have an ethyl group. On the third carbon, and then on the third carbon again, we're going to put 2 methyl groups. And the main chain itself is going to be 7 carbons long, making it a 4-ethyl 3,3-dimethyl heptane. I want you to try the next one. Note that this way, either way you number it, we're going to get 3 as the lowest number. As a rule of thumb, we like the lowest number to be first. So whichever one of these is alphabetically first, give that one the lower number if it's the same either way. I really wouldn't get finicky about this. But you know what I mean? Like you can either count this way, in which case the methyl will be carbon number 3, or if you count this way, the ethyl will be carbon number 3. The preferred of those two would be giving the ethyl the lower number, but that really is not something I'm going to stress about if you get it wrong. Yeah?
With all these CH bonds, at what point does it stop being like a ethyl or a heptane or whatever?
It doesn't, in the sense that like even a 52 carbon chain has a name. I can't think of what 52 would be off the top of my head. But as long as it's a chain of single bonded carbon to hydrogens, we're going to call it an alkane, even if it's a big unwieldy one. And they do get very big and unwieldy. And we sometimes will then have even bigger naming systems. So for example, when we get to sugars, you could name sugars with this naming system, and they're not wrong, but sugars then have their own naming system to make life easier.
It's a different naming system then.
That's right.
Like different,
That's right.
that makes sense.
I think that's right. Yeah, I think that's right.
You just like know all of the names.
Calvert knows everything. Like legitimately, the man knows everything.
3, he asked what a 42-sided shape was called, so we looked it up, and it was called a tetracantachydegon, because it was tetra 4, conta 10, so 4 tens, chi, di, so 4 tens and 2 gone. And so he memorized that because he found it very interesting. So in kindergarten, when the teachers all asked what your favorite shape was, that's what he said. I was very proud of him. Triangle, circle, tetracantachydegon for who is this kid? Awesome.
I like it. I have a cousin who's the same age as my eldest children, and she's very impressive. She has given speeches at the UN. She's been canoeing with Justin Trudeau. She met Obama. She spoke right before Greta Thunberg once. She single-handed. She literally wrote the law that became the paper straw law, which I don't hold against her. And from the environmentalist in me appreciates it because I'm an environmentalist. But the part of me that hates. So she's very impressive. And her parents, who are my aunt and uncle, are always sending me Fia's on the CBC today, and they send me a speech. And then my wife and I have a text chain where as soon as we get one of those, we send it. Then immediately I'll go take a picture of Claire asleep at 3 p.m. in a really messy room, which is bad. But anyway, so we have this whole text chain of contrasting our children with my cousin Sophia. Anyway, that's the end of my story. All of which is to say, when my kids were 3, they were not telling the teachers that tetra. Anyway, it's all good. Point being, and my kids are lovely and highly successful. So, it's all good. But highly is a sliding scale. Anyway, moderately, capably, yeah. Anyway, Fia gave a speech to Mark Carney just 2 days ago.
Oh, wait,
He's our prime minister.
Wait, he is?
Did you not know that?
Oh my!
I thought it was so distant.
Let's focus. Let's focus. I mean, in fairness, you still see that bumper sticker everywhere. Anyway,
Wait, is that why
sad.
the YouTube ads for the election stopped?
Did you not know what was happening?
No, I don't pay attention to that.
I weep for my.
No, I hated
Who's the prime minister of
In
India?
this school?
Oh, Mahatma Gandhi.
Okay.
Yeah.
Okay.
Shut down for 3 days.
Anyway, the important thing is that the future of our nation is doomed. But the good news is, in the short term, we can still do basic organic chemistry.
What did you have for civics? Oh, what's your problem? The civics and careers, so you learn about first past the post, electoral system.
Oh, I think I had Miss Miano.
He asked how much did you get?
Oh, How much?
No, I asked you, who did you have?
No, but I want to know what you got. Did you pass? Did you pass with a 90 in civics?
Hell yeah, I did.
No, you're not. You passed like a 60.
Yo, don't rat me out.
I'm pretty sure you did.
No, that makes sense. Listen, I prefer to hear that at the moment.
Those are the group chat. That's enough.
Do you know there's no more important thing? Like, listen, if you look, like, dude, like, man, do you know that there are fewer people living in stable democracies today than there were 50 years ago? Which is a pretty depressing thing to think about because the population of the earth has come close to doubling in that span, but there are fewer people living in stable democracies today than 50 years ago. We take for granted that you live in a country where you can say what you want, where you can post what you want, where you can hold what opinion you want. You want to drive around with a bumper sticker that says F the leader of our country? You can do that. It's a little gauche, it's a little trashy, I think, but you can do it. Nobody's going to stop you. Try that in Russia. See how that goes for you. You know, try that in Iran, see how that goes for you. Try that all over the world and see how it goes for you. People get killed. You know, Russia, famously, people get killed and the family gets billed for the bullets. You know, like, we take for granted that we live in a nation, that you have a democracy, and we're cynical about it, and we're miserable, and we complain about it, and we think, politicians lie, and they don't do this or that. You get to pick them every 4 years, 3 years, 5 years, whatever the time span is. We're not on a nice, neat schedule like the States. We have a parliamentary system. But even still, if you're not happy with them, you get to decide who is them. And if you're really not happy with them, you can go run and do it yourself. I have all kinds of friends who got into politics. My buddy Cameron, he's ran for mayor and keeps losing in Hamilton, but he's a town councillor, right? He's on that. My father-in-law was a town councillor in Lincoln for years and years, and you get to be the person making the decisions. That's a gift. It's a gift. People die. People die crossing oceans and crossing continents to try to get places where they have that available to you. And like I'm not picking on you, but the us in general, myself included, knowing a little bit about how your country works and getting involved and engaged is an important thing. Because in the end, a few years from now, it's going to be your generation that makes the decisions. And I got news for you. The generation before us, you can decide for yourself how good a job they've done. I have some problems. My generation, starting to step into power. We don't exactly seem to be bringing the best things about. It's going to be your turn one day, you know? And it's going to be seriously. And in a couple of years, it's your turn to start being a part of who decides, who leads. And by the way, part of the reason people healthily ignore, part of the reason you get to be cynical and go, they don't do anything for us anyway, is, politicians ignore people in their early 20s when it comes to deciding what their policies are going to be. Do you know why? Politicians who are out seeking votes to try to remain in power ignore you guys. No, but by your 20s you can vote. But you know what you guys don't do a lot? Vote. You vote in the lowest number of any age group. So why would they pay attention to you? You're not signing their meal ticket, right? And Canada should be pretty embarrassed. Our participation in elections is an embarrassment by international standards. I have a friend who lives in Switzerland. I think they had 93% voter turnout in their last elections. 93% of people turned out and voted.
Good morning, East on today's cafeteria
So,
menu.
yeah.
We have the super big chili
Yes.
for $2.
4 diethyl 3 methoxy.
It's just a single ethyl, because di would mean that there's two of them. Yep, that's an ethyl group. Other than that, you're good. And then usually we'd give this the 3 and that the 4, though your name isn't wrong. Like if you switch the numbers.
It's not diethyl, it's just 1 ethyl.
That's right. This is a single ethyl group, so 3 ethyl, 4 methyl. And then how long was the main chain? Is this a 7 again?
6.
1, 2, 3, 4, 5, 6. Yeah, great. Thank you. That's right. If you put another ethyl up here, that would make it a diethyl. And you'd have to name them both. So it would be a 3,3 diethyl. And you could put an ethyl here if you felt like it, in which case it would be a 2,3 diethyl. And you could put an ethyl here. Well, you actually couldn't, because if you put an ethyl here, the longest chain wouldn't be 6 anymore. Then the longest chain would be 7, and you'd actually call this a heptane. But yeah.
What if, theoretically,
Yep.
for like one of these chains, at the end it's just a carbon, and like say like 3, what is it, like methyls or something? Will we have to like write it?
So the one thing to know about that is you actually can't have a methyl group on the end. And that's not because it's against the rules. It's just because, okay, say this is my chain, and now say I put a methyl group here. Well, what have I really just done? I've just made the chain longer. Do you know what I mean? So that's like, you can't have a 1-methyl. You can't have a 1-anything. Because if you throw something on the first carbon, it just becomes part of...
Oh, the longest. Okay.
It just becomes part of the chain. Does that make sense? Now, if you put 3 methyls on there, then actually now, those are going to be side groups, but they're no longer on carbon 1. Now they're considered to be on carbon 2, because we call that the start of the chain. So the thing with that, it's just a naming convention, which is we always name the thing after the longest chain you can make. And if you shove something on the first carbon, now it's not the first carbon anymore. Now it's the second carbon. It's part of the chain. Does that make sense?
Yeah.
Cool. All right, guys, you're doing good with this. That's great. We'll finish it up tomorrow. Have a wonderful day. Be kind to one another. Don't do anything Alex wouldn't do. You just, honestly, I always just go like, is that the longest chain? 1, 2, 3, 4, 5, 6. So that's actually tied for longest chain, but I'm not going to use that because then my branch would have a branch. So it's not wrong, but it's going to be a mess. Does that make sense? The answer to so many of these things is not wrong, better way. Right? Not wrong, but there's a better way.
Didn't you just do it like the opposite way? So if you made an L,
Yep, you could do that, which gives you the exact same structure, which is you still have an ethyl on carbon 3 and you still have a methyl on carbon 4. So that is actually, those are congruent structures, or they're symmetric, like they are the same. The only reason they look different is because we've chosen to draw this in a straight line. But of course, we know in reality, nothing's a straight line. It's all, the angles aren't 90, the angles are exactly. How you doing, kid? Yeah. Did you have volleyball yesterday?
I had it on Tuesday.
Is it 1 day a week?
2 days a week.
2 days a week. So Tuesdays and
Thursdays.
nice. And then games?
We have a